All right, so we are talking about acceleration. And today what we're going to be talking about is how to find how far an object moves during a period of acceleration when you know certain other things about the object. In these cases, we always have to know how fast the object is going to begin with, the initial velocity. But as long as we have three properties about the object, we can find out how far it goes. So first we're going to start off with finding the displacement, how far it moves, when the velocities and the time period are known. So this V should actually be VI and VF. So basically what we're going to be doing today is taking some equations and then deriving other equations from them. So this is kind of a math lesson. So we'll start out with our equation for velocity. And remember, this equation is for average velocity. We know that average velocity is found by taking the displacement divided by the time interval. So when we rearrange that for displacement, we have average velocity times the time interval. Now, another way to find an average is to add up the number of things that you have and then divide by that number. So if we have an initial velocity and a final velocity, that's two velocities. So another way to find an average velocity is by adding the two velocities together and dividing by 2. Or we can express that as 1/2 of VF plus VI. So by placing this into this equation for average velocity, we end up with displacement is equal to 1/2 of VF plus VI times t. And we can verify that using a velocity time graph, which I will show you how to do on the next slide. So here is a velocity time graph, and as you guys might remember, the displacement of an object during a period of acceleration, or well, from a velocity time graph, can be found by taking the area under the curve. So we're going to cut this. This is the graph of an object with constant acceleration on a velocity time graph. We're going to cut this into a rectangle down here and a triangle up here. So the rectangle would have an area of base times height. So if we think about that for a sec, Ted, we've got a base of our time interval, and the height is our initial velocity. Okay? The triangular portion up here, area would be 1/2 of base times height. So that would be 1/2 of the base is still our time interval, and the height is our final velocity minus our initial velocity. So VF minus VI. Now, I'm going to do just a little bit of rearranging because it doesn't really matter what order you multiply things together in, right? So I'm going to rearrange this to 1/2 of VF, VF minus VI times t. And then if I distribute the 1/2, I'd have 1/2 VF minus 1/2 VI times t. And then if I go ahead and distribute the t, I'd have 1/2 of VF times t minus 1/2 of VI times t. So this is the area of the top portion, and we have to add in the area of the bottom portion, which is just, I'm going to rearrange that also, VI times t. So if we add these two things together, we'd have 1/2 of VF times t. And then if this is basically a negative 1/2 VI times t, if we add a positive whole VI times t, negative 1/2 plus positive 1 would be positive 1/2, right? So we end up with plus 1/2 VI times t. So then we're going to take the t and the 1/2 back out. Put the 1/2 out in front. VF plus VI is what's left on the inside, and t behind it. Displacement is 1/2 of VF plus VI times t, verified by using the velocity time graph. Pretty awesome, huh? This is one of those classes where if you're just a teeny bit nerdy, you can gain a little bit of an appreciation for math. All right. I'm not going to do any example problems or anything in this. I'm going to save those for class time because I think that would be best. So we're going to move along to what if we don't know what the final velocity is? We have to know what the initial velocity is. I mentioned that before. So we have to know when the initial velocity, or what the initial velocity is. But what if we don't know the final velocity? We only know the acceleration and the time interval. In that first problem, we didn't know, or that first equation, we didn't have the acceleration. Okay? So in this problem, we have the acceleration, but we don't have the final velocity. So if we start with that equation that we just figured out, 1/2 of VF plus VI times t, and then we play one of my favorite games, the substitution game. We've got this equation in our last set of notes, VF equals VI plus AT. So if we substitute, since we don't know what the final velocity is this time, if we substitute VI plus AT into this first equation for VF, then we get this big mess right here. 1/2 of VI plus AT plus VI times t. So again, here we are going to distribute the t, and we end up with 1/2 of VIT plus AT squared plus VIT. Well, if we think about that, we see 2 VITs in there. So we can stick those together and call it 2 VIT. So we'd have 1/2 of 2 VIT plus AT squared. Then we can distribute that 1/2, and that leaves us with VIT plus 1/2 of AT squared. Half of 2 would be 1, and then half of the AT squared would be 1/2 AT squared. So another way to find an object's displacement during a time of constant acceleration, if we don't know what the final velocity is, we can use VIT plus 1/2 AT squared. This last little thing just says that at a constant velocity, a displacement time graph shows a parabolic curve. That was just kind of in that spot in the book, so I threw it into the notes. Again, we'll save example problems for class time. So, what if we know both of the velocities, initial and final? And the acceleration, but we don't know the time interval. Well, in that case, since we know that acceleration is found by taking VF minus VI over t, we can rearrange that for t, and t is equal to VF minus VI divided by a. Then, going back to that first equation we found today, we take 1/2 of VF plus VI times t and substitute this in for the t. We end up with 1/2 of VF plus VI times VF minus VI all over a. Now, if you're multiplying by 1/2, you're really dividing by 2. So I've simplified that by writing it this way: VF plus VI times VF minus VI all over 2a. Then what we do, we go back to algebra class and FOIL the top part here. VF times VF would be VF squared. Here we have a plus VI times VF and over here we have a minus VI times the VF. Those would cancel each other out. And then we have plus VI times negative VI, which would be essentially negative VI squared or minus VI squared. And it's still all divided by 2a. So, let me get rid of these circles. Another way of finding displacement when you don't know the time interval is taking VF squared minus VI squared divided by 2a. Now, for some reason, they don't like to leave equations with fractions if they don't have to. So they rearrange this equation, and you'll typically find it written out like this. VF squared equals VI squared plus 2AD. What they're doing there is multiplying both sides by 2a to make 2AD, and then adding VI squared to both sides to leave VF squared by itself. Again, we'll leave that stuff for class. We'll talk just a little bit about gravity, because gravity is an attraction between the Earth, which is an extremely large mass, and all of the other objects around it. There's a, you guys might remember from Earth science class. It was kind of funny, wasn't it? You guys remembering stuff from Earth science class? Anyway, you should have talked about Newton's law of universal gravitation and gravity, there being an attractive force of gravity between any two objects in the universe based on their masses and how far apart they are. So anyway, Earth is an extremely large mass. We all have masses. All of the objects on the Earth have masses. So there is an attractive force of gravity between the Earth and every object on it, which causes all objects to fall. And this is the cool part, that all of the objects fall at the same rate of acceleration. Probably should throw that in there, rate of acceleration. When we can ignore air resistance. Air resistance kind of messes things up. But for our purposes, we're going to always consider objects where we can ignore air resistance. So the acceleration due to gravity is constant. And that's what all these equations we just figured out are, is for constant acceleration. And that constant is about negative 10 meters per second squared. This does vary slightly between different parts of the Earth just because the Earth is not perfectly round. So if you're closer to the equator, you're actually farther away from the center of the Earth than you are if you're closer to one of the poles. Because gravity depends on the masses and the distance between their centers. So if you're toward the equator, you're farther away from the center of the Earth, which makes gravity just a little bit less. Go up on top of a high mountain, go way up in an airplane, you're a little bit farther away from the center of the Earth. Gravity is a little bit less. So since gravity makes things accelerate at a constant rate, then there's some things that we can assume for objects that we can ignore air resistance for. That is, any object that's being dropped has an initial velocity of 0. So if you see a problem where it talks about something as being dropped, the acceleration, the thing that's going to make it fall toward the Earth, is gravity. So the acceleration can be replaced by the acceleration due to gravity, which is negative 10. And its initial velocity is going to be 0 meters per second. Because if you're holding it just up in the air, it's not moving. The very instant that your fingers let go of it, it's still not moving, and then gravity takes over very quickly and starts to pull it downward. So its initial velocity is 0. Any object that is thrown up into the air or falling downward through the air is accelerated by gravity. If you throw it straight upward, then you have an initial velocity of positive VI. Again, if you're dropping it, then its initial velocity is 0. If you throw it upwards, then its initial velocity is in the positive direction, because up is positive, and it's traveling at whatever speed you threw it at. When it goes up in the air, gravity is pulling downward on it, so it's got a positive velocity, negative acceleration that's going to make it slow down to a stop. Things go up in the air, they stop at the very top of their flight before they start to fall back down. So if we consider the top of their flight, the VF would be 0 meters per second at the very top. Okay, so those are some things, some assumptions we can make for objects being dropped or thrown through the air. And again, we will save example problems for class time. So that is it. See ya.